It's 3 a.m. You're in bed. The room is dark, the fan is on, and you're in that perfect half-asleep state where absolutely nothing can go wrong. Then the sky outside your window turns white. Not sunrise white, not lightning white. A flat, total wall of light white. The kind that means something very large is moving very fast directly toward the thing you're standing on. That thing is a rogue planet. A world with no star, no orbit, and no reason to exist in your neighborhood. It has been drifting through interstellar space for 4 billion years, and it has spent exactly 0 of those years caring about you. Here's what makes that worse. Scientists estimate there are more rogue planets in the Milky Way alone than there are stars. Some estimates say 20 times more. Today, every single one of them is headed here. And I need to walk you through exactly what happens next.
To understand how badly this goes, you first need to understand what a rogue planet actually is, because it is weirder and more unsettling than most people realize. A rogue planet is a planetary mass object that was either ejected from its original star system during formation or formed entirely alone in interstellar space without ever having a sun. They are cold, dark, and completely invisible to standard telescopes because they emit no light. The only way to detect them is by the way their gravity bends light from background stars, a technique called gravitational microlensing, and even then, you get a signal that lasts a few days before the object disappears back into the dark. In 2023, the James Webb Space Telescope found over 540 free-floating planetary mass objects in the Orion Nebula in a single observation. Not 5, not 50, over 500 in one look at one small section of sky. Some of them appear to be orbiting each other, pairs of rogue worlds wandering through space together, bonded by gravity, going nowhere in particular. The most recent population estimates, built from microlensing surveys, suggest that the Milky Way contains somewhere between 10 billion and 100 billion rogue planets. The honest answer is that we do not know where in that range the real number sits. What we know is that the lower bound is already more than the number of stars in the galaxy, and the upper bound is 10 times that. These objects range from the size of Mars to several times the mass of Jupiter. They travel at speeds relative to the galactic center of around 20 to 50 kilometers per second, though their speed relative to any individual star system depends entirely on the geometry. Some would arrive fast, some would arrive very fast. None of them announce themselves in advance. Now imagine every one of them simultaneously arriving here.
The problem does not begin with the direct hit. Most rogue planets will not hit Earth directly, but they do not need to hit us to cause catastrophic damage. They need to pass close enough to disturb our orbit, and the threshold for close enough is a lot wider than you might think. A Mars-sized rogue planet passing through our solar system at 0.5 AU, roughly half the distance between Earth and the Sun, would exert a gravitational pull strong enough to nudge Earth's orbit by a meaningful margin. It would just need to pull and then leave. The problem is that Earth's current orbit is calibrated to within extremely tight parameters for habitability. The distance from the Sun, the eccentricity of the orbit, the axial tilt, these are not arbitrary. They are the specific conditions under which liquid water exists on the surface. Seasons remain moderate, and the climate stays within the range that life has spent 4 billion years adapting to.
A 5% change in orbital distance does not sound dramatic. It would mean average surface temperatures shifting by roughly 7 to 10 degrees Celsius globally. That is the difference between the current climate and a full glacial maximum. Ice sheets down to the mid-latitudes, sea levels 120 meters lower, and agricultural zones reduced to a fraction of their current area. And that is the mild version from a small rogue that only passed nearby. But even that mild version assumes only one rogue planet came through. In this scenario, they are all coming. The gravitational interference from hundreds of thousands of objects passing through the inner solar system would not produce a neat shift in one direction. Earth's orbit would become unpredictable. The Sun is still there. You still have a sun, but the orbit Earth takes around it is no longer the orbit that created you.
But the small rogues are not the most dangerous thing here. Not even close. A significant portion of the rogue planet population consists of superjupiters, objects several times the mass of our own Jupiter, which is itself 318 times the mass of Earth. When one of these objects enters a solar system, it does not just nudge orbits, it reshapes them completely.
Jupiter has spent the last 4 billion years acting as a gravitational shield for the inner solar system. Its enormous mass deflects or captures comets and asteroids that would otherwise reach the rocky planets. The Earth's relatively stable impact history, as opposed to the Moon's heavily cratered surface, is partly a record of Jupiter doing its job. Remove Jupiter's gravitational stabilizing influence, or worse, overwhelm it with a competing mass, and the inner solar system's debris environment changes immediately. A Jupiter mass rogue passing through the outer solar system at close range would scatter the Kuiper Belt, the vast field of icy bodies beyond Neptune, sending millions of objects onto new trajectories. Not all of those trajectories lead outward. Many of them lead inward. The asteroid belt between Mars and Jupiter would be similarly destabilized. What currently exists as a distributed, mostly stable field of rocks would become a funnel of projectiles pointed at the inner planets. This is not speculation. We have strong evidence that something similar happened in our own solar system approximately 3.9 billion years ago, during a period called the Late Heavy Bombardment, a several hundred million-year interval during which the inner planets were struck by an unusually high number of large impactors. The leading hypothesis is that a gravitational reshuffling of the giant planets caused it. Jupiter or Saturn moved. The inner solar system paid. In our scenario, that event is not a chapter in geological history. It is happening right now. At some point in this scenario, one of them hits. To understand the scale of a planetary collision, the most useful comparison we have is the one that created the Moon. Approximately 4.5 billion years ago, a Mars-sized object called Theia collided with the early Earth. The impact was not what you might picture if you imagine a large rock hitting a smaller one. It was a collision between two planetary bodies at tens of kilometers per second. Both objects were partially or completely vaporized. The mantle material of both worlds was thrown into a disk of molten debris around the remaining core. That debris coalesced over time into the Moon. The energy released in a planetary collision at interstellar approach velocities is orders of magnitude larger than any event that has happened on Earth since. A rogue planet striking Earth at 30 kilometers per second, a conservative estimate for interstellar velocity, would release energy equivalent to roughly 10 to the power of 31 joules. For context, the entire Sun outputs about 3.8 times 10 to the power of 26 joules per second. A single rogue planet impact would release in an instant the equivalent of tens of thousands of seconds of total solar output.
There is no crater. There is no extinction event. There is no surviving biosphere to be extinguished. At a certain impact size and velocity, the distinction between the impactor and the Earth stops being meaningful. They become the same object, a sphere of liquefied, vaporized, recondensing material before the physics of reassembly begins. What comes out the other side depends on the size and angle of the impactor. A Mars-class rogue hitting Earth at an oblique angle might produce something like a new moon, a partially reformed world with a large satellite, an eccentric orbit, and a surface temperature in the thousands of degrees. A Jupiter-class direct hit does not leave a planet. It leaves a debris disk around the Sun, slowly cooling over millions of years, which will eventually, if given enough time, reassemble into something smaller and different, starting over. No memory of what was here before.
But let's run a more interesting version. Let's say none of the rogue planets hit directly. Let's say Earth gets lucky, repeatedly, and every rogue planet passes close enough to pull, but not close enough to destroy. What does a world look like after surviving that kind of gravitational battering? There is a real scenario, studied by planetary scientists, in which a close gravitational encounter between two objects results in one of them being ejected entirely from its home system. The visiting object transfers momentum to the resident, and the resident, in this case Earth, gets thrown outward. Not inward toward the Sun, outward, past Mars, past Jupiter, past the heliopause, into interstellar space. At that point, Earth is no longer a planet of the solar system. It is a rogue planet. Life does not automatically end in this scenario. It sounds like it should, but the picture is more complicated. The surface would freeze within decades as Earth moved away from the Sun. Average surface temperature would eventually stabilize around -240 degrees Celsius, close to the cosmic background radiation temperature. Nothing on the surface survives that. But under the surface, there is still a geothermal heat gradient driven by radioactive decay in Earth's core. That heat will persist for billions of years, regardless of whether there is a sun nearby. And where there is heat, liquid water is possible. And where liquid water exists in rock, certain microbial life can persist.
The irony is that if Earth was ejected and became a rogue planet, and life survived in deep geothermal vents for long enough, and something eventually happened to warm the surface again, a captured brown dwarf, a close stellar encounter, anything, the planet that eventually re-entered a stable orbit around a new star would still be carrying life. Changed beyond recognition, adapted to 4 billion years of cold and dark, but alive. Which means the thing that just tried to kill you, the rogue planet flying past in the middle of the night, might itself be carrying passengers from somewhere else, frozen deep, waiting, not dead, just in transit. And that changes everything about how we think about this.
Here is what the rogue planet situation actually means, once you understand the numbers. The Milky Way contains somewhere between 10 billion and 100 billion of these objects, moving through the galaxy in every direction, at speeds between 20 and 200 kilometers per second, completely invisible. No star, no light, no warning. The solar system has been in existence for 4.6 billion years. In that time, it has almost certainly had close encounters with rogue planets. We just have not detected them because the encounters happened before humans existed. And the gravitational records of those encounters are buried in the statistical noise of orbital dynamics we are only beginning to be able to model at the level of detail required.
The James Webb Space Telescope is finding hundreds of rogue planets per observation field. As survey sensitivity increases, the population estimates are going up, not down. The most recent models suggest the real number might be at the high end of the range, closer to 100 billion than 10 billion. We are discovering, slowly, that the dark parts of the galaxy are not empty. They are full of worlds that belong to no one, going nowhere in particular, at speeds that would end this story before you finished your next sentence. Tonight, somewhere between here and the nearest star, there is a planet-sized object with no name and no sun, moving through the dark at 40 kilometers per second. We do not know where it is. We do not know where it is going. We do not know if it is heading toward us, away from us, or somewhere in between. And you will not know until the sky outside your window turns white again. Sleep well.